Swayam Prabha. Digital India. Educated India.
It is with great honor that I would like to introduce the lecturer, Professor Mangal. Professor Mangal is a professor from the chemistry department and specializes in a vast array of topics, including quantum chemistry, magnetic resonance, and many others. He obtained his PhD in theoretical chemistry from the McGill University, Montreal in 1988 and has spent several years in Canada as a postdoctoral research fellow before returning to India as a faculty in IIT Madras. In addition, he is also one of the founders of the NPTEL project and has been associated with it since 2001. We welcome you, sir.
Thank you. So, thank you very much for the introduction that you gave. This is the nice thing because it's the shortest introduction given, and I'm very happy that it stopped with that. It shouldn't say anything else beyond that. And the other thing I wanted to tell you is that chemistry is the life of all sciences, okay? And engineering, technology, and also the real life that we think about. Chemistry is the underlying phenomenon in every aspect of what we live today. So I sometimes have students who come and tell me, chemistry is very difficult, sir. I find it very, very difficult. I don't like it. I don't know. As I said, I'm very happy that even if you don't like chemistry, that chemistry still likes you because you are walking alive. Otherwise, you won't breathe. Your chemistry, if it is dead, then bacteria will take care of you and you are no longer there. Every part of your living, there is a chemical connection to that. Right from the fact that atoms and molecules were proposed from the time, and when many people did not believe that atoms and molecules do exist, but something called the phlogiston which exists, not atoms and molecules. And there was a theory for phlogiston, and there were only 4 elements or 5. Almost like what we have in our philosophy, Prithvi, Apu, Deyu, Vayu, Agaso. Something like that, earth, fire, water, and what's the 4th element? Yeah, okay. So something like that. Everything belonged to that. And there were people who believed in that. At the same time, Dalton came up with his most important conceptual idea of the existence of atoms proposal, and also he proposed properties for that. Another 3-4 decades later or 5 decades later, the periodic table was put forward by Mendeleev. Incomplete periodic table. He could not fill the table according to the kind of organization that he had. He could not fill with all the elements known at that time. But still he left it for the future to determine and fill up that. And today we have a periodic table which is called the long form. Approximately 120 elements are listed there. Now you think about maths. It's a human thought process, but it is not independent of real life. Mathematicians are very, very close to real life when they think about extremely seriously about their results. This is not my statement. Professor Hardy had made something similar to that in his book. Hardy was the person who brought Ramanujan to the front line in England. So mathematicians obviously, they give theories, they have methods and so on, but a lot of it somehow was found to be very relevant to the physics. And you had today morning Professor Bala talk about basic aspects of physics. And physics, we always say, is the philosophy of science, in the sense we try to find out the fundamental laws which govern the whole universe. And we are still in search of them. Okay, some laws we think we know, the other laws we do not have ideas on. and we are not able to patch up different discoveries of physics still as one unifying method. We are still towards that. And in 1900, of course, when Max Planck came up with his proposal for the quantization of the energies which were transacted by the black body, at that time, a lot of physicists believed that everything that was to be known had been known, and except for some 4 problems that they were not able to understand. And one of them was black body radiation. The other was the spectral lines of the hydrogen atom in emission. Why they were lines rather than absorption all around. Why light is not absorbed or light is not emitted in all frequencies by the hydrogen atom. And then there was this photoelectric effect which was around that time. So people said, oh, these are small things. Okay. Those 3 small things made the whole world different in the next 100 years. Because people who concentrated and tried to attend and to understand them, lots of people followed, and eventually, you see, after Max Planck, after Niels Bohr, after Albert Einstein, and Erwin Schrödinger later, Heisenberg, Dirac, Max Born, so many others. You saw the whole new physics came up, which now had to relate the phenomena of small objects that we cannot see by naked eye. But we have to understand them. The problem is, the small objects that we have, chemistry had already said at that time 92 such small objects are there. 92 uranium at that time was still known. Its atomic number is 92. Okay? And of course, it's an isotope. There are different atomic masses. So if you think about maths, most of the current maths is decided by 10 numbers, 0 to 9. We live in a decimal system for most of the world. Okay? There are parts where they don't use the decimal system, but they use very similar to that. And then we also have what is called standards system international. They are all in tens, 0 to 9. The much later discovery was the computer with 2 lights on and off, okay? 0 and 1. Even today, 0 and 1 are the 2 numbers which run the whole world. Okay? What is 0 plus 1 is something that people are looking at a lot of. It's not 0 plus 1, but some number times 0 plus some number times 1. Is that a state? That's what is called the quantum state, okay? Which is supposed to form the basis of quantum computers. It's neither 0 nor 1, but some combination of 0 and 1. And when you repeat that for multiple systems, you have 1 qubit, 2 qubits, multiple qubits, and then you have 64 qubits, 128 qubits, 246. Okay? They are all powers of 2. 2 numbers, 0 and 1. Okay? But chemistry provides, that's the biology. Everybody thought that biology largely is about understanding plants and animals, and through some system of, what is that called? Taxonomy. Lower level systems and then higher level and so on. So the taxonomical buildup of the nature. And then later, biology, people realized that there is a molecular basis to that, and there is a microscopic basis to the atomic and molecular basis to biology. And then it was proposed in the 20s and last century, 20s and 30s, that the genes are the most important, probably carriers of information of life and genetics. Okay. Before that, the genetics was known in a certain fashion, but the fact that the genes were becoming important, and that the DNA, deoxyribonucleic acid, and the RNA, that these are fundamental constituents, and DNA is the one which carries the information. RNA is one which transfers and which synthesizes these kinds of things. This kind of biological input came in the middle of the last century. And then everybody looked at, then therefore, that if they are the most important thing, then how do we replicate ourselves? Why do our children look like the way we are? Why do generations of it? So the moment you wanted to understand the reproduction and the growth and all the other things, one started looking at the structure of the DNA and RNA and all these things. And of course, then came the most famous discovery in 1953 or 52, around that time. James Watson and Francis Crick came up with the model for the double helical structure of DNA. And that was not just a human thought process, but that was strongly supported by experimental findings of X-rays, X-ray structures provided to them, which they had unique access, but which another very famous scientist at the time did not have that access. Linus Pauling did not have that access. These two had the access, and they came up with the most beautiful fundamental discovery of the structure of the genetic code, what genes are. And then you realize DNA consists of only 4 letters. Okay. If mathematics is about 10, 0 to 9, and everything else can be built out of that, and then you extend that to continuous numbers, you extend that to complex numbers, you extend that to irrational numbers, rational numbers, and so on. Those are all extensions, but starting with the integers. You had 10. And computers have only 0 and 1. And biology has 4 letters. A, T, G, C. And if you want RNA, you have U. So 4 plus 1, 5. Still, you see how biology progressed with 5 manipulatory objects. Okay? Now imagine a chemist in his toolbox has 92 objects, which are very different. Everyone is independent. It is not that all 92 are equally present in a large amount on the earth. Why are we still looking at the objects, astronomical objects, and we are looking at the planet, the stars and other things for life, for other materials and so on. We want to find out what is there. Are these the only things, or are there other things? So if you think about chemistry, it is not enough that you follow physics and mathematics and use them, but you must also be able to predict the properties of these 92 elements, which when they combine, in what ratios they combine, why do they combine, why do they not combine, and when they do, how do we understand the reactions, the reaction mechanisms, and is there a way of quantifying all these things into buckets of knowledge so that they belong to one or the other? Okay. At the end of the day, our knowledge has to be systematized into, I understand this part, all of this belong this way. Behave this way. I understand this part, all of these behave this way. We can do that. Chemists have 92 elements to live with. So the challenge that chemists has is far more enormous than the challenges that the computer scientists had, or even the biologists had. Biologists have to look at the combinations and the variations of all of them. But if you remember, if 5 such quantities can produce so much variation, what are the possible variations of these 92 elements if we are able to do synthetic? Therefore, you see, chemistry is the most important one. Okay? You have to learn many, many more things about the 92 elements, the atomic structure, and so on. Of course, a lot of these chemistry methods are based on physics, based on mathematics. But in addition to all of these things, in parallel, in today's lecture, for about 10-15 minutes, I'll talk about one very important aspect of all these molecules, that they all have, most of them at least, a symmetry, proportions which are equal on either side, or on rotating a molecule, or on reflecting a molecule in an imaginary plane and things like that. Molecules have symmetry. Molecules have structure and shapes. Tetrahedral molecule, all of you know, CH4, methane is the most famous example. Or any carbon connected to 4 identical atoms. mono, single bonded, 4 identical atoms. It's a perfect tetrahedron. And then we have octahedral molecules. And then today morning I just typed, what is the most symmetric molecule? What's the answer?
Carbon, no, the Buckminster Fuller.
Yeah, that's what Google gives me. Okay, I assume that is probably true. But if all these atoms were continuous and if the connectivity happens together, it's spherical. But no molecule is spherical, because a sphere has no particular point that you can locate. Everything is continuous. Whereas fullerene and the larger size fullerenes and even bigger, and finally the geodesic domes of the Buckminster Fuller, who built all these things in the early days. I mean, they are all essentially models which emulate a sphere by adding more and more points to a spherical structure. If the points are completely filled up and they are continuous, they become sphere. Okay? So today we think that there are carbon-60 is probably the most symmetric. But you should be surprised if you did not know that Plato knew this, not carbon-60. But Plato had the Greeks, they ascribed to 5 Platonic solids. What are they? Square is the first one, then cube. Okay, cube. No, cube, tetrahedron, octahedron, dodecahedron, and icosahedron. These are the 5 Platonic solids. The symmetry, if you think about it, symmetry in terms of our understanding of what is symmetric, if we have to write, the symmetry of icosahedron and the symmetry of carbon-60 are the same. 2,500 years ago. But we didn't classify it that way. Which one? Come again?
Sir, icosahedron is with 20 or 30 sides? 20.
Okay, now dodecahedron will be, they both have the same symmetry, dodecahedron and icosahedron. They have the same symmetry. Dodecahedron is dodeca, 12 faces and 20 vertices and 30 edges. So now you can imagine why carbon-60, when you talk about how many pentagons does it have, carbon-60? It has 12 pentagons. How many hexagons does it have? 20. Connect that. Okay. Icosahedron and dodecahedron have the same symmetry in terms of, I'll show you. Today I'm only going to discuss one symmetric object. Okay. Maybe we'll read more about it later. And why it is important? Why should we worry about molecular symmetry? Okay, I have a molecule called CHClBrF. Okay, carbon bonded to 4 different elements. No symmetry at all. Each bond length is different. It's not a perfect tetrahedron because the interactions between chlorine and hydrogen will be different from the interactions between hydrogen and fluorine. Is not at all symmetric. That's the other extreme. Okay. Or if I say HDO instead of H2O. Okay. Hydrogen, water with 1 deuterium instead of 2 deuteriums. That's a D2O. Water with 1 deuterium. Again, it's not symmetric in a real sense, that you cannot have the kind of symmetry that I will explain to you. So when you talk about a symmetry, at least in physics and chemistry, you talk about the objects having certain proportions when you perform mentally some operations like rotating the object or reflecting the object through some planes. The planes don't exist. The lines don't exist, but imagine that there is a line and then you perform a rotation about that line. And if you do that and the molecule becomes identical to what it was after doing this, other than a 360-degree rotation. Because any object that you rotate 360 degrees, any physical object, you rotate by 360 degrees about any axis, it becomes the same. So that's the equivalent of 1 in multiplication and 0 in addition. You need them, but that's redundant. But apart from that, suppose you have a molecule like water. You can imagine that this is symmetric about a line which bisects the bond. Okay. So if you rotate this molecule about this axis in a plane perpendicular to this line, okay, by 180 degrees, this hydrogen atom 1 and 2, if you can mentally distinguish them, they become 2 and 1. Okay. Both are identical. So the line that we can imagine, which is a line that sort of bisects and the rotating by a certain angle, 180 is important because if you do one more 180, one goes to exactly where it was earlier. So 2 180s is equivalent to the identity. But this element of our imagination that the molecule possesses is called a symmetry element for the molecule. And as you go look at more and more molecules, you come up with more and more such symmetry characteristics. And why are they important? They are important in understanding the molecular properties of those molecules over a period of time. These relationships are built up, and they are important in understanding the dynamics of the molecules. Why molecules absorb certain energies, why they don't absorb certain other energies. If you want to look at them, symmetry also gives us some knowledge about what is allowed and what is forbidden transitions that molecules undergo when you shine radiation on it. So symmetry as a whole, this is a new phenomenon. The idea of symmetry was known to humans for hundreds and thousands of years. Beautiful objects have been built which are symmetric. You know, Tanjavur temple, you go to Madurai Rajaraja Solan temple, or you go to any, even Rameswaram temple, you can talk about symmetry objects. And man is almost symmetric, but for the fact that there is only one heart. That's the only difference. But from, if it is left, right, and 2 legs, 2 eyes, nose, sort of you draw a line in the middle. Approximately the left half and the right half sort of look as mirror images, approximately. But here it's not approximation. The left half and the right half, if you think about it, okay, they are identical. Now, what about this molecule? No, I think you are used to this kind of picture, right? What does this mean? They are towards you, okay? So, okay, can think about it. So you can think about it like the sort of the 3 hydrogens forming an umbrella down and the chlorine up. You hold the carbon molecule, this molecule by the chlorine top, and you rotate by 120 degrees. The 3 hydrogens form the base of an equilateral triangle. Okay. If you project them to a plane, all the 3 hydrogens will form the corners of an equilateral triangle. Therefore, you can see that the hydrogen, the chlorine is sort of pointing towards you. If you want to think about it, that you have the 3 hydrogen atoms in the plane of this board and the chlorine is pointing out. Then you can rotate this by 120 degrees about to the CCl. So the line CCl, 120 degrees, is a symmetry axis. Okay. Is there any other symmetry axis? No. No, none. It has one axis about the CCO. Because if any axis towards the CH, of course, those three atoms will not go into their equivalent positions. They won't. Chlorine will move somewhere else, hydrogen will move this way, hydrogen will move. And the molecule is not the same as before or after your sort of a mental picture of looking at whether it has a symmetry or not. Therefore, you see, the symmetry was conceived in molecular systems in terms of lines and, of course, in terms of planes. Okay? A plane perpendicular to the water molecule, a plane perpendicular to the board. If you reflect, the two atoms reflect onto each other. Okay? Is there any other plane? All molecules which are planar have the plane of the molecule as a symmetry element. Okay. Nothing happens when you reflect the molecule on its own plane. Suppose the molecule is in this plane and you consider this as a symmetric plane, nothing happens. That's what you think. But please remember, molecules are not static. They are constantly moving. All molecules above 0 Kelvin are vibrating relative to each other. And they are also rotating about various axes. They are translating. All molecules above 0 Kelvin. Therefore, if water molecule is a very simple example, but in this case, for example, is there a plane of symmetry here? What is the plane? What is the plane? What does the plane contain? So, one Cl carbon and one hydrogen. If you do that, the other two hydrogens will be exactly on the mirror image positions on either side of the plane. So, there are three planes there. Okay. In water molecule, you have a plane of the molecule, you have a plane of the perpendicular to the plane of the molecule, and you have a line. These are the three things about which water is symmetric when you perform what you call mentally asymmetry operations. And these are important in a sense that they were found to be following the same mathematical outcomes of group theory. Okay. These symmetry elements have very close connections to the mathematical group theory, particularly what are called the discrete group theory, point group theory. And the application of that, including the molecular orbitals and the atomic orbitals, became a very beautiful subject over the last 70, 80 years. Okay. To study molecular systems which have certain symmetries. So the carbon 60 has phenomenal amount of symmetry elements. Okay. Let me quickly look at one of the more symmetric objects of Plato, that is called the tetrahedron. Okay. What I have done is to put the tetrahedron inside a cube. Okay. So that the carbon, for example, the center molecule, whatever it is, okay, is the body center of the cube. The other two are on two corners on the face. They are along the face diagonal. You take, there are 6 faces here in the cube. This one on the back, this one, top and bottom. There are 6 faces. All these points are face diagonals. Okay. This face diagonal. The diagonal on this face is these two. The diagonal on this face is those two. This point is here, that point is behind. Okay. Now this is tetrahedron. Now, you know how many symmetry elements that we can consider, symmetry, things that we can, symmetry operations, how many things, each rotation is considered an operation. For example, this operation is a 1/120 180-degree rotation. You do once more, it's usually denoted by the line C, by the symbol C2. Okay. If you do another C2, it's like doing them together. Obviously, you will get nothing other than identity. E is called identity, that is 360-degree rotation, or reflecting something in the plane twice. You reflect them once, 1 goes to 2, 2 goes to 1. You do one more reflection, 2 goes to 1, 1 goes back to 2. So, if you do that reflection, this is usually written by the symbol sigma. Okay. Which one? What is it?
What is represented by sigma?
The plane. The plane, there are two planes. So, there is a sigma, and to differentiate this, maybe you call the sigma prime. The plane of the molecule has one symmetry element, and the plane perpendicular to the bond is another symmetry element, and the line here is actually the meeting point of these two planes. Please remember, the intersection of these two planes is the line. Okay. So whenever you have these kind of perpendicular planes, you will see that the intersection also has a symmetry element. So another thing is that the beauty of this kind of visualization of molecular structure in the mental framework is that the presence of certain symmetry elements mean the presence of certain other symmetry elements as well. Okay. Just now I said, if you say this molecule has this plane of symmetry and this plane of symmetry, it will have to have a line of symmetry about which it will rotate by 180 degrees. It's inherent. So the presence of certain symmetry elements mandate the presence of other symmetry elements. Okay. And these are mental constructions. But please remember, the whole of theoretical description of molecular structure, molecular properties is a mental construction based on quantum mechanics, verified by experiments and substantiated through mathematical arguments. And the mathematics is the mechanics associated with that. So here also, the elements that you have, they have some connectivity between them. So in the case of tetrahedron, we'll go one at a time. What do you think is probably the most symmetric element for a tetrahedron? If we say Cn, what is the largest value for n? 3. What is that 3?
So for that tetrahedron or
For the tetrahedron. Where is that 3? I told you that these 3 atoms, which are identical, form the corners of an equilateral triangle. No. This is 1, 3. Rotate about that 180 degrees, sorry, 120 degrees. You get these 3. This goes here, and that comes here. Okay. So you can see how they go into equivalent positions. Sorry, don't worry about that. That's the next step. So there are 3. How many C3s are there in that case? There are 4 of them. Okay. No, it's not C12. Each C3 is different.
So we can't like 4 C3.
4 C3 elements, 4 objects. You can think about that. But the C3 automatically means something else.
3 planes of symmetry for each of them.
3?
3 planes of symmetry.
No, the line itself. First, let us stick to the line. We'll not worry about the planes. Planes will come back later. The presence of a 120 degree rotation as a symmetry element also means the presence of 240 degree rotation. Please remember, 360 is the only identity. Any angle which is a fraction or an integer divided is a symmetry operation. So if it is 120, 240 is also a symmetry operation. So each C3 gives rise to 2 elements of symmetry. A C3 and a C3 and a C3 done twice, square. And there are 4 of them. All 4 are independent. So how many are there? You have 8 elements of symmetry, rotational symmetry. Okay, 8 C3. Okay. Now, how many planes? Now we'll come back to your planes. Where are the 6? Right. So if you do this, if you choose 1 and 2, the reflection is of 3 and 4. So you have 1, 2, 3, 4. How many pairs can you, independent pairs can you make? That's right. So 1, 2, 1, 3, 1, 4, and yeah, this picture can be misleading because it's giving one direction asymmetric height. But remember, in a tetrahedron, it's isotropic in space. All 4 directions are identical. So if you take any pair, the reflection on the plane containing that pair, the other 2 will reflect. And therefore you have 2, 3, 2, 4, and a 3, 4. So your answer 6 sigma is right. Okay. Then any other element, any other plane, any other axis that you can think of. Yeah, now the cube picture may help you. Let's go back to the cube picture. Yeah, go ahead. Yeah. How is it? How is it 8? Okay. A rotation by 120 degrees is one operation. Rotation by 240 degrees is also by the same operation, right? 1, 2, 3, they are identical atoms. So 1 goes to 2, 2 goes to 3, 3 goes to 1. Do one more rotation. 1 which went to 2 now will go to 3. But if you do 360, it's identical. Therefore, there are 2 rotational operations with one axis. A C3 and a C3 done twice. How many C3s are there? About each bond. Each bond is 1 C3. There are 4 bonds, identical bonds. So you can choose this axis. You can choose this axis. You can choose that axis. Any of them. Because tetrahedron is spatially isotropic. Okay. Therefore, your X, Y, Z doesn't matter. All directions are identical. All the 4 atoms are in an identical spatial location. So any pair of them, that axis. Therefore, you have 8C3. Okay. Yeah. Now, I'm going to look at something else. Yeah. I guess let me do this. Let me open this with the VLC, but I will stop this right now. Okay. What about that line? Is that a symmetric line?
Yes. So that is a C2 symmetry.
That's a C2 symmetry. As you rotate by 180 degrees, what happens to 1 and 2? 1 and 2 are, the 3 and 4 will go into themselves. What about these 2? You are rotating the whole molecule. So whatever is tight will rotate, rigid. It's a rigid rotation. Therefore, you see there is one axis. It's one C2 axis. Right? How many? How many? It's cube. You have put a tetrahedron inside a cube. And how many mutually orthogonal axes in 3 dimensions? Those are the 3 mutually orthogonal axes. You know, the second orthogonal line will be this, the third orthogonal line will be this. But now you see, this is not 1, 2, 1, 3, 1, 4. This is simultaneously rotating 1, 2 and 3, 4. Okay? 1 and 2 will go to 2 and 1, and 3 and 4 will go to 4 and 3. Therefore, how many of them are there? There are only 3 possibilities. 1, 3 and 2, 4. And 1, 4 and 2, 3. You see, the binary combinations immediately reduce the numbers. Because simultaneously all 4 atoms change. So you have 3 such axes. So what you can see is this axis. See that? So that's a C2. Okay. That's a C2. Right? So that's one more. So now we have 6 sigma, 8C3 and 3C2. Okay. Identity, that is doing nothing or doing a 360-degree rotation, is always there. What else do we have? This is something you would not know unless you have studied before. See, sometimes it is possible for a molecule not to have a line of symmetry or a plane of symmetry, but a combination of those two. What is it? Center of symmetry is fine. That is one more. Center of symmetry is one. That's the next one. That's next one. That's the next one. I'm talking about, you will see something here. See, let me do a rotation of this molecule by 90 degrees. This one. If I do rotation by 90 degrees, what do? One goes to, yeah, no, it doesn't give you the same configuration.
Yes, sir, but which rotation are you referring?
Any axis, the 3 axes that you have, the C4, C2 you have. So instead of doing 180 degree about that axis, let me do a 90 degree. What happens? 1 goes to the empty spot. 2 goes to the empty spot here. But in the bottom, please remember, these 2 again go to the empty spot. Now you do a reflection perpendicular to that line. Okay. A rotation followed by a reflection perpendicular to the plane. Perpendicular to the line, to the axis, rotation axis. Let's see. Rotation by 90 degrees, a reflection gives you, please remember, it gives you the same molecular structure, same positions of identical atoms before and after the rotation and reflection together. Okay. Go back. See. Now you do the reflection. This becomes identical to what we started with. Right? The rotation brought the molecule to a different spatial arrangement. It's not the same thing as what you said. Suppose you looked at the molecule before and say, I do a 90-degree rotation, you will see that the atoms are not in the same place, identical atoms. Therefore, you see that you have not done a symmetry operation. A symmetry operation brings the molecule to an indistinguishable spatial configuration. So you can see that 90 degrees by itself does not do. The plane by itself does not do, because if you reflect these atoms in the plane, they will go to the opposite edges. These two will go to the vacant edges, those two will go to the opposite edges. Therefore, the reflection is also not an element, but the combination of the two is an element.
Reflection followed by rotation.
Rotation followed by reflection.
Is this commutative?
They are commutative. Yeah, they are commutative. Yeah, they commute with each other. You can do either way. You can reflect and then you do rotation. Try that. I mean, mentally you can immediately see that those two are the same.
Swayam Prabha. Digital India. Educated India.